learn how to factor a matrix in a way that's very useful for making large computations quicker and easier. So remember the definition of factoring, like when you take a polynomial and you factor it, it means you multiply it, you rewrite it as a multiplication problem. So that's what we're going to do. We're going to learn how to factor a matrix. So you write it as a product of other matrices. We're going to look at one brief example of a computation that's made easier by using this special factorization, but there are many, many more. This special factorization is called diagonalization, and it's a powerful tool. You'll probably see it again, but we're just going to do one application of it today. Okay, so I already diagonalized matrix A. So this is just a 3x3 matrix, and the special factorization called diagonalization. It's called diagonalization because the middle matrix is a diagonal matrix. It has only entries on its diagonal. Everything else is 0. And then the other two, so we call that one D. And then the other two matrices we call P and P inverse. They're actually inverses of each other. Okay, so we can rewrite any matrix, well, not any, many matrices A you can rewrite in a diagonalized factorization, P times D times P inverse. So the way you find P, D, and P inverse, basically you just need to find P and D, and then P inverse you find by taking the inverse of P. So D is made up of entries on a diagonal, and those entries on the diagonal are eigenvalues. So the eigenvalues of A are 3, 6, and 6. And then the entries of P are the eigenvectors that are associated with each eigenvalue. So the eigenvector associated with lambda equals 3 is in the corresponding column of P, right? So the 3 is in the first column of D, which means if you look at the first column of P, that's an eigenvector associated with lambda equals 3. Okay, and you only need one. And then the eigenspace is just the span of that guy. It's all multiples of that. So for lambda equals 3, the eigenspace is the span of 1, -3, -1. Now, if you were trying to find D and P, right? So D, you just find you find the eigenvalues by solving the characteristic equation, throw them into D, and then you just need one eigenvector to put in P, and it can be any. There's an infinite number of them. You can just pick any one you want and put it into the first column of P, the corresponding column that the eigenvalue is in. So by looking at P, you know the entire eigenspace. And then for lambda equals 6, 6 appears in 2 different columns of D. So those 2 columns of P are both eigenvectors. They're linearly independent eigenvectors that go with lambda equals 6. And the eigenspace is the span of the 2 of them. Uh, 0, 1, 1. And 2, -1, 0. So if you get, when you're doing this in the reverse, if you're asked to find P and D, if you have an eigenvalue that appears twice, has multiplicity 2, then it needs to have 2 linearly independent eigenvectors to go with it in order to be able to diagonalize. If there were only one free variable when you're trying to solve for the eigenvectors, then you can't diagonalize it. There's no way to do it. So your 3 columns of P, or all your columns of P, need to be linearly independent. Mm-hmm. Yes. Yes, or like you can write 3 and 6, and you'd say 3 multiplicity 1 and 6 has multiplicity 2. You can write it like that as well. All right, so that's the factorization. So I didn't go through we kind of did backwards of what you're typically going to be asked to do in a homework problem or in the activities. You'll be asked to find D and find P. So we sort of did it backwards. D, you just throw the eigenvalues on the diagonal. P are the eigenvectors associated with each of those eigenvalues. So what this factorization is good for is raising a matrix to a power. So if I wanted to evaluate a to the fourth, that means a times a times a times a. So I could actually do that out, right? So I would have to do 7, -3, -1, 2, 0, -2, -2, 6, 8 times again. Right, and then 2 more times. So to multiply a 3 by 3 times a 3 by 3, that's going to be 3, 6, 9, 12, 15, 18, 20, 19, 20, 21 multiplications, right? So that's a lot of calculations. And if I wanted to do a to the 20th, right, it might even take a computer a long time, right, when you start having large matrices and raising them to high powers. So my shortcut is that if you have it in diagonalizable form, if you've diagonalized A, you can raise a to the fourth by doing P times D to the fourth times P inverse. And raising a diagonal matrix to a power is really easy. You just raise each entry to the fourth power, which is not true for a non-diagonal matrix. So you just do a to the fourth is P, which is 1, -3, -1, 0, 1, 1, 2, -1, 0. D to the fourth, you just can take each entry of D and raise it to the fourth. So this is 3 to the fourth, 0, 0, 0, 6 to the fourth, 0, and 0, 0, 6 to the fourth, times P inverse. So this saves us one whole matrix multiplication. Saves us 9 individual multiplication problems. So it doesn't appear to be that big of a time saver in this case, but when you're doing big matrices and high powers, this is going to save you a lot of computing power. So we don't have to actually figure it out, but just so that you can see that it would save you time.